Sir, good morning, sir. Sir, good morning, sir.
Good morning.
I'm Krishnan.
I'm not able to recognize you now. You look very different in your photograph. How are you?
Every sir, how is life?
I don't hear well now. You see, I can't.
Good morning, everyone. I welcome you all to Day 3 of Science Academies 6-day online lecture workshop organized by the Department of Physics, St. Philomena's College, sponsored by the Indian Academies of Sciences. We have with us Professor R. Srinivasan to deliver his lectures today, so we shall begin immediately.
Okay. Good morning to all of you. Yesterday, I talked to you about the formation of energy bands when an electron moves in a periodic potential. At some points in the Brillouin zone, you find that the energy of the electron is not continuous. There are some energy states which the electron cannot take. Now, in a semiconductor, the topmost band is completely filled and the band above that is completely empty at absolute zero. At a finite temperature, some electrons can be excited into the conduction band from the valence band, and this gives rise to the electrical conductivity of the semiconductor. In a metal, on the other hand, the topmost band is only partially filled, so the metal has a large number of electrons which can take part in the conduction, and so its electrical conductivity is very large. The minima in energy or the maxima in energy which occur at different points in the Brillouin zone. I am going to talk about how to expand the energy as a function of K about the minimum or the maximum, and this gives rise to the effective mass approximation. Oh, yeah. See, near a maximum or minimum of energy, for example, minimum in the conduction band or maximum in the valence band, that will occur at a wave vector k0. So the condition for maximum or minimum is gradient of E with respect to k at k is k0 will be 0. That means if k has components k1, k2, k3, delta E by delta k1 must be 0, delta E by delta k2 must be 0, delta E by delta k3 must be 0. At a minimum or a maximum of the energy, So around this value of K, namely K naught, you take some other value of K close to K naught, then we can expand the energy E at K in terms of the difference in wave vector K minus K naught. This is the Taylor expansion, which all of you know. So E at K is E at K naught plus first derivative with respect to K multiplied by K minus K naught I. But first derivative with respect to K is 0 at a maximum or a minimum. So that term is 0. The third term is half summation over I and j, second derivative of A with respect to Ki, Kj at K naught multiplied by K minus K naught ith component into K minus K naught jth component. Then there will be higher power terms, third order, fourth order, etc. terms. So near a maximum or a minimum, when K is very close to K naught, then this term is the most important term and higher order terms are less important. You can see that this quantity delta square E by delta Ki delta Kj is a second rank tensor. It is a second rank symmetric tensor because delta square E by delta Ki delta Kj is the same as delta square E by delta Kj delta Ki. So it is a symmetric second rank tensor. But I want to avoid all complications in the presentation. So I will assume that this second order derivative is 0 when the component K, I and J are different. And when I is equal to J, you will get three terms: delta square E by delta K1 square, delta square E by delta K2 square, delta square E by delta K3 square. I will assume all of them are equal and they have a value alpha. Then you see that Ek will be Ek naught plus half alpha into K minus K naught I whole square plus K minus K naught 2 whole square plus K minus K naught 3 whole square, that is value of K minus K naught whole square. Now if I write like this, there is some similarity to the motion of a particle, free particle. Motion of a free particle, energy is proportional to K square. Here energy is, the difference in energy is proportional to the square of the difference in the wave vectors. So you can write the parameter alpha as h cross square by m star. So m star will be a parameter which will have the dimensions of mass. So this quantity m star actually is a parameter which gives the curvature of the energy versus K surface at K equal to K naught. It is a parameter which will give you the curvature, but this parameter has the dimension of mass. We call this the effective mass. Let us try to understand why this mass will be different from the actual mass of the electron. The electron is moving in a crystal, then under the action of an electric field. So there is an external force due to the electric field acting on the electron. There is also an internal force because of the periodic potential of the lattice. So you write the Newton's equation. The mass of the electron into dV by dt is F external plus F internal. F external is the force due to the electric field. Suppose F internal is proportional to F external. Suppose F internal is beta F external. Oh. No. Suppose F internal is proportional to F external, then this equation becomes me dV by dt is 1 plus beta F external, or m star dV by dt is F external. This looks like the equation for a free particle of mass m star acted upon by an external force. So you see that the effective mass origin arises because of the internal force in the material. This argument you take with a pinch of salt. It is a hand-waving argument to show you that m star arises due to external force, but you will not always have F internal equal to proportional to F external. Let us now take this approximation to the energy, and let us take the minimum of the conduction band where you have a few electrons. The electron has a negative charge. So I write the charge on the electron as minus modulus of E to show that the charge is negative. In an electric field E, the external force on the electron minus modulus E into the electric field E. The external force is opposite to the electric field. So near the minimum of the energy, the curvature is positive. So m star is a positive quantity. So I now write m star dE by dt is minus E. This will be the motion of an electron at the bottom of the conduction band with a mass different from the mass of the electron under the action of the electric field. But if you take the valence band, it has a maximum. At the valence band, curvature is negative. So m star is negative. How do you interpret a negative effective mass? So if we substitute in the equation, I write a negative effective mass as minus magnitude of m star. So if I now substitute in the equation m star dV by dt is minus modulus E, it will become minus modulus m star dV by dt minus E is equal to minus modulus E. I will cut off the negative signs on both sides. Then it looks as if it is a positively charged particle with a positive mass moving in the electric field. So at the top of the valence band, it is as if the motion of the electron is as if you have a fictitious positive particle with a fictitious mass moving in the electric field in the direction of the electric field. This fictitious particle we call as a hole. A hole actually should have no mass, but we attach a mass to the hole, so it is a fictitious particle with a positive mass and a positive charge, and it is actually only the electrons moving, but at the top of the valence band, the motion of the electrons can be equated to the motion of a positively charged particle moving in the direction of the electric field. To illustrate this, I have shown how the electrons move in a field, in a conduction band, and in a valence band. There is a conduction band. There are a few electrons in the bottom of the band, shown as red circles. The other energies are not occupied. This is E versus K near the minimum of the band, which I call as 0. I put K naught is 0. The momentum of the electron is h bar k. So, under the action of the electric field, the momentum h bar k changes. So, rate of change of momentum h bar dk by dt is minus. Charge on the electron is negative. Force is minus E. So, what will happen to the k value for the electron? K value for the electron will decrease. This is the direction of the electric field, positive x. So K will change in the negative x direction. So the K value will decrease. So the electrons with negative K, they will go to higher energy. Electrons with positive K will vacate their higher energy states. So you will see there are more electrons with negative K values moving to the left than with electrons moving to the right when you apply an electric field. So the negative electrons carry negative charge to the left. So there is a net more charge transport of electric charge to the left. Negative charge to the left, that is equal to a positive current to the right. So the effect of the electric field is to produce a positive current in the direction of the field, though the electron is moving to the left. Now we take a valence band. The valence band goes down and down. There is a peak. The electrons fill all energy levels. There are a large number of electrons. These are the unfilled states. Now you apply an electric field. The electrons with positive K will reduce their K value. Electrons with negative K will increase in energy. Electrons with positive K will decrease in energy. So the electrons here will decrease in energy. Electrons here will increase in energy. So these empty states will get filled. These states which were occupied will now become unoccupied. So you again find there are more electrons on the left side than on the right side, giving a positive current. But now you have to deal with a very large number of electrons. You now look at what happens to the unoccupied states. When you apply a field, number of unoccupied states on the left become less than the number of unoccupied states on the right. If you say unoccupied states carry a positive charge equal to the electronic charge, then you see there will be a, if you take only the unoccupied states, it will correspond to a transport of positive charge to the right. That means a current to the right. The excess number of holes is the same as excess number of electrons. So they give the same current. So you can describe the current in a valence band when you apply an electric field, either in terms of the motion of the very large number of electrons or in terms of the motion of the very small number of holes, assuming the holes to carry a positive charge and a positive mass. You see that this description in terms of holes involve a few holes, and therefore it is easier to talk in terms of holes than in terms of the motion of a large number of electrons. So near the top of the valence band, we use the fictitious concept of the whole because it is easier to talk in terms of a fewer number of holes, but it will give you the same current as talking about the large number of electrons. So that is the advantage of the concept of a hole. The hole actually does not have a mass. The hole actually does not have a charge. But we imagine it carries a positive charge, it carries a positive mass and moves in the direction of the electric field. The conduction band, there are a few electrons, many holes. So description of the current in terms of motion of electron is convenient. In the valence band, I have to say valence band here. This is wrong. In the valence band, in the conduction band, there are many electrons. No, I think I have written this sentence is wrong. Forget about it. In the valence band, there are a large number of electrons and a few holes. So the description in terms of holes is convenient. This is valence band, not conduction band. Then M star is inversely proportional to the curvature. A small M star means a very large curvature. Energy is changing very rapidly with K. So the K values go up to the end of the Brillouin zone. So the width of the energy band will be very large when the effective mass is small. So a small effective mass indicates a large bandwidth. A large effective mass indicates a narrow bandwidth. It is not proportional, inversely proportional to the effective mass. It is an indication. A narrow bandwidth corresponds to a large effective mass. A large bandwidth will correspond to a small effective mass. The effective mass description is useful in semiconductors because in semiconductors there are a few holes in the valence band and a few electrons in the conduction band. If you take an intrinsic semiconductor, an electron is raised by thermal energy to a valence band, leaving a hole. So the number of holes is the same as in the valence band is the same as the number of electrons in the conduction band. Both of them contribute to the electrical conductivity. This is called an intrinsic semiconductor. But you can dope a semiconductor with a dopant which has a different valency. For example, silicon has a valency of 4. So you can dope silicon with boron, which has a valency of 3, or with phosphorus, which has a valency of 5. Phosphorus has 1 electron more than silicon. Boron has 1 electron less than silicon. Such doped semiconductors are called extrinsic semiconductors. So if you dope with boron, it has 4 neighboring silicon. You see, every silicon is bound to its neighbors with 4 pairs of 4 bonds, each bond containing 2 electrons. If you put a boron, this boron will donate 1 electron to this silicon, 1 electron to this silicon, 1 electron to this silicon. There is a hole in this bond. So this hole will act as a hole in the valence band, and this will conduct electricity. So if you dope with a trivalent material, you create holes in the valence band. You call it as a p-type semiconductor because the carrier of charge is the hole which has a positive charge. If you put phosphorus, it has 5 electrons. It donates 1 electron to each of the 4 bonds. It has 1 more electron which goes into the empty conduction band and it transports charge there. So here the charge carrier is the electron which is negatively charged. So we say it is an N-type semiconductor. So by controlling the amount of doping, you can control the conductivity of the semiconductor. Now I talked about effective mass. How do you measure the effective mass? This you do by an experiment called cyclotron resonance. I apply a magnetic field. A charged particle is moving like this at an angle to the magnetic field. So it has a velocity parallel to the magnetic field. It has a component perpendicular to the magnetic field. The magnetic field will exert a force on a moving charged particle. The force is charge Q into V cross B, where V is the velocity vector of the charge and B is the vector giving the magnetic field. So the force due to the magnetic field is perpendicular to the velocity of the magnetic field, perpendicular to the direction of the magnetic field. Because the force is perpendicular to the velocity, it does no work on the electron. Because in a time dt, the electron moves this way, force is perpendicular. So the work done is F dot displacement. Displacement is perpendicular to the force. So the magnetic field does no work on the electron. Its energy does not change. But because of the force, the direction of the velocity changes. So you see that the charged particle will move in a helical path along the magnetic field. Because it has a component, there is a component of the velocity parallel to the field which is not affected by the magnetic field. The electron moves this way. It also moves in a circle, so the motion is an ellipse. If you project this ellipse on a plane perpendicular to the magnetic field, then you get a circle, and the projection, the point of projection goes round the circle again and again with a frequency, angular frequency omega, which is the magnitude of the charge into B by m, the mass of the particle. So if you measure this frequency, you can measure the effective mass. To measure this frequency, you shine a laser beam with the same frequency omega. The laser beam with a frequency omega. You change the magnetic field. When the cyclotron frequency EB by m becomes equal to the laser frequency, then the charged particle absorbs energy from the laser beam. So you can measure the absorption of energy. It will become a maximum when the laser frequency matches the frequency of the cyclotron resonance. And that you can control by adjusting B. So you change B. Then when B cyclotron frequency matches the resonant frequency, there will be a absorption. If you take an electron and if you apply a field of 10 power 4 Gauss, 1 step, then this angular frequency 176 gigahertz. So you see to apply to measure cyclotron resonance, you have to use a far infrared laser beam and you have to use a very high magnetic field of the order of 100 Tesla. So the experimental arrangement for cyclotron resonance is this. You have a far infrared laser that is the 36 micrometer water vapor laser. The light coming from the laser is chopped. That means you have a disk with a hole. The disk is rotating, so it allows the laser beam to pass through when the hole comes across the beam, and it obstructs when the hole moves away from the beam. So the laser beam will fall on the sample periodically depending on the angular frequency of the chopper wheel. If the chopper wheel moves 1000 rotations per second, the light beam will be interrupted 1000 times in 1 second. Then the light beam is taken through a light pipe and falls on the sample, which is kept at low temperatures. This is a coil of copper to produce a magnetic field. But the magnetic field is not produced by sending a constant DC current because you need a field of the order of 100 Tesla. The current involved will be very large. Your copper coil will burn out. There is a coil and you discharge a bank of condensers which are charged to high voltage. You connect it to the coil. Charge on the condenser will be discharged through the coil in a very small time, microsecond, producing a very high current. So the magnetic field will increase with time, reach a high value, and then will decrease when the charge is reduced to zero. But this high current produces so much of heat that the coil will be destroyed. So you have to put another coil and again charge the capacitance and discharge it. And when the magnetic field increases and when the frequency matches the laser frequency, cyclotron frequency matches the laser frequency, the transmitted beam is absorbed. You have a detector to measure the intensity of the transmitted beam is absorbed. You see that you will get two peaks, one when the magnetic field is increasing and one when the magnetic field is decreasing. So you get two peaks symmetrically about the maximum. And these are the cyclotron resonance peaks, which will give you the effective mass. So this is the trace of the detector showing absorption as a function of the magnetic field when there is in Gauss as a function of the magnet. There is in frequency as a function of the cyclotron frequency. You see different peaks due to holes. What happened? Due to holes and electrons. You have two different holes with two different effective masses, and you have two different electrons with two different effective masses. This is for silicon. Why are you getting two different values of the holes? I told you that in silicon there are two valence bands which are slightly split due to spin orbit coupling. One valence band is flat, so the hole has a heavy mass, and the other valence band has a larger width. So this other valence band gives the smaller hole mass. Why do you get two electron masses? The minimum of the conduction band in silicon occurs along the 100 direction. If it occurs at plus B00, by symmetry, there will be 6 minima in the Brillouin zone at plus minus B00, 0 plus minus B0, 0 plus minus B. There are 6 equivalent minima in the conduction band at 6 different points in the Brillouin zone. And if you look at delta square E by delta K1 square, it is different from delta square E by delta K2 square and delta square E by delta K3 square. It means your E K is EK naught plus alpha times K1 square plus beta times K2 square plus K3 square. So you make a constant energy surface. What is the surface in K space on which the energy is constant? It will not be a sphere. If E is proportional to K square, then whatever be the direction of K, energy E is the same if the magnitude of K is a constant. So constant energy surface when E is proportional to K square is a sphere. But if E is not proportional to K square, it is alpha K1 square plus beta K2 square plus K3 square. The constant energy surface is an ellipsoid of rotation. It has different curvatures corresponding to different effective masses. You have one effective mass which you call as a longitudinal effective mass and two other effective masses corresponding to transverse effective mass. So these are the two effective masses of the electron, longitudinal and transverse. The longitudinal effective mass is 0.98 times ME and transverse effective mass is 0.19 ME. And as you change the direction of the magnetic field, the value of the effective mass will change. This is very complicated because I have to explain how the electron will move. So if this is my ellipsoid, constant energy surface is an ellipsoid, and if this is my magnetic field, you take a plane perpendicular to the magnetic field, that will cut the ellipsoid at an angle, and that will give an ellipse. The energy will move, the electron will move along that ellipse in a plane perpendicular to the magnetic field. Motion of the electron will not be a circle, it will be an ellipse. And as the angle of the magnetic field changes corresponding to the axis of the ellipsoid, the section of the ellipsoid will change. So the ellipsoid shape will change, and that will give rise to different longitudinal and transverse masses. This is very complicated, but you can make very precise measurement. You can make very precise measurement of the effective masses using cyclotron resonance. So I want to go to the next chapter. You must go to and go to the next file. Yeah. Yes, go to the number density of state. I will. Okay, so I have told you what is the effective mass approximation, how it is useful in the case of semiconductors where you have few charge carriers, in the conduction or valence bands, and how you can measure the effective mass using cyclotron resonance. Now I will go to my last talk, number density of states and Fermi level. I will consider a free electron inside a cube of side L. So the electron is a free electron, so it is represented by sin kxx e to the power of I kxx into e to the power of I kyy into e to the power of I kzz. That will be the wave function for the electron. Kx, ky, kz are the components of k square. K square is kx square plus ky square plus kz square. The energy is h bar square k square by 2m. Because the electron is inside the cube, the wave function must vanish on the planes x is 0, x is 0, x is L. Y is 0, Y is L. Z is 0, Z is L. It is a cube, so the wave function must vanish on these sides. This means you must make a wave function by superposing plane waves e power ikxx, e power minus ikxx, e power ikyy, e power minus ikyy, etc., so that the boundary condition is satisfied. Wave function is 0, x is 0, y is 0, z is 0. So such a wave function is sin kxx, sin kyy, sin kzz. You put x is 0, it will vanish at all values of y and z. So it vanishes at the phase x is 0. You put y is 0, it will vanish at all points, x and z. At y is 0, it vanishes on the face y is 0. Now, the wave function must also vanish at x is L. So sin kxl must also be 0. So kx must be an integer times pi by L. If you put kx is nx pi by L, when x is L, kxx becomes nx pi, nx is an integer, so sin n pi is 0. Whatever be the values of y and z, so it will vanish at x is L. So the boundary condition that the wave function vanishes at x is L imposes the condition that kx must be nx into pi by L. Similarly, ky must be ny into pi by L. Kz must be nz into pi by L, where nx, ny, nz must be positive integers. If all of them are 0, there is no wave function anywhere in the box. So at least one of them must be non-zero and they must all be positive integers. If you put a negative integer, that comes out. And you know a wave function can be multiplied by plus or minus. It else represents the same wave function. So it makes no difference. So nx, ny, nz must be positive integers. So this tells you all values of k are not possible. Only those values of k are possible for which k is nx pi by L, comma, ny pi by L, comma, nz pi by L. And correspondingly, ek, which is h cross square k square by 2m, is h cross square pi by L, the whole square by 2m into nx square plus ny square plus nz square, which we write as n square. So I take nx, ny, nz axis. I mark points. Nx is 0, nx is 1, nx is 2, nx is 3, ny is 0, 1, 2, 3, nz is 0, 1, 2, 3. Only at these points, any point, this will be a lattice. Any point in this lattice will give you an allowed value of k, because any point in this lattice, nx, ny, and nz are positive integers. So in nx, ny, and z space, this lattice in the positive octant of the space gives you the allowed wave vectors and energy values. The number of wave vectors and energy values will be very large. And therefore, because my L is very large, I take a macroscopic box. This macroscopic box has a size 1 meter. The wave vector is 1 by L. So it will be 1 by meter. And you can have wavelengths going all the way from 0 up to the edge of the box. So you have a very large number of wave vectors, allowed energy values in this box. So instead of counting how many allowed energy states, I count how many allowed energy states are there between E and E plus DE. What should I do? I draw a sphere of n value n corresponding to the energy E. You see, E is proportional to n square. So for a given E, I will have a given n. So I draw two spheres, n and n plus dn, corresponding to the energies E and E plus dE. So dn will correspond to the change in the number when I change the energy from E to E plus dE. So these two spheres will enclose a spherical shell, which will go all over the space because I am drawing a sphere. The sphere is in all the 8 octants of space. But I take only the positive octant. I take the shell in the positive octant. I count the number of points in this positive shell. Each point gives you an allowed energy value. So the total number of points in this positive shell will give me number of energy values between E and E plus dE. So you see that a sphere has a volume 4 pi n square. The sphere n plus dn will have a volume 4 pi n plus dn whole square. If dn is very small, the volume between these two spheres will be 4 pi into you differentiate n square 2n dn. 8 pi square n dn is the volume of the spherical shell between the sphere of radius n, sphere of radius n plus dn. But out of this total volume, I must take 1/8 the volume in the positive octet. So 8 pi n dn, I must take 1/8 of the volume of a sphere, is 4/3 n pi n cubed. I made a mistake. 4 pi r square is the surface area. Volume is 4/3 pi r cubed. And therefore I differentiate it. I get 4 pi n square dn, and I must take 1/8 of this volume of the shell. So 1/8 of 4 pi n square dn. Then I must count how many points are there. The points are equally spaced. For example, you will get a point when nx changes by 1. You will get a point when ny changes by 1, when nz changes by 1. So if you take a cube, you will have nx to nx plus 1, ny to ny plus 1, nz to nz plus 1. You take a cube of side 1, you will get points at the corner of the cube. Each point is shared by 8 cubes. So each cube, 1 point will belong to it. There are 8 corners, each corner shared by 8 cubes. So this cube will get only its share, 1/8 into 8, or 1 point. So there will be 1 point in a volume of unity. This volume is 4 pi n square by 8 dn. So how many points will be there in this volume? It will be 1/8 4 pi n square dn into 1, because there will be 1 point per unit volume. So you see the number of energy values, between E and E plus dE is given by 1/8 4 pi n square dn. Now you substitute for n in terms of E and substitute for Dn in terms of dE, then you get the number of energy states is L cubed 2m by h bar square pi square power 3 by 2 into 4 pi by 8 e power half dE, or it is L cubed into this pi square power 3 by 2 is pi cubed, 4 pi by 8 is pi by 2, so 1 by pi cubed multiplied by pi by 2 will be 1 by 2 pi square, and then 2m by h square power 3 by 2 e to the power of half dE. So I can define a number density of states. How many states are there for unit energy interval? I put dE is 1. How many energy states are there? That will be NE. That is called the number density of energy states. NE is this. So NE will be L cubed 1 by 2 pi square 2m by h cross square power 3 by 2 e power half. So the number density of states for a free electron will vary as the square root of the energy, and it will be proportional to the volume L cube. If I take a box which has twice the volume of the original box, there will be twice the number of states in that box. I hope you understood this derivation. You followed this derivation. It is very simple. Now we come to the Pauli principle. These are the energy states or quantum states for an electron. For the free electron in the box, what are the quantum numbers? Nx, Ny, Nz. These are the quantum numbers which specify the energy. They are the quantum state numbers for the state E. But in the state E, you can put two electrons because the electron has an intrinsic quantum number, which is the spin quantum number half. And this spin quantum number can either be pointing up or pointing down. They will have the same energy. So in the energy state Nx, Ny, and Z, you can put two electrons because the spin can have a projection plus or minus half. Therefore, Pauli exclusion principle states that for any energy state of the electron, there will be two electrons. Therefore, in the 1s state of an atom, you can have a maximum of two electrons. In the 2p state of an atom, you have three states. Px, L is 1, L is 0, L is 1, and L is minus 1. Ml is minus 1, Ml is 0, Ml is 1. There are three states. In each state, you can put two electrons. So in the p state, you can put 6 electrons. Same way here, for each Nx and Y state, you can put 2 electrons and not more than 2 electrons. So total number of electrons maximum will be twice the total number of filled states. Now I come to the statistics. Because we are not working at t equal to 0, we are working at a finite t. Pauli exclusion principle says maximum number of electrons you can put in a state, but if you are at a finite temperature, the number can be less than the maximum number because thermal energy can raise the electron from one state to another state. So we have to deal with statistics. Particles obeying the Pauli-Dirac principle, they obey Fermi-Dirac statistics. So at t is 0, we can fill each quantum state. A quantum state is specified by Nx and Y and Z and Ms. So you have two states, Nx and Y and Z plus half, there will be one electron. Nx and Y and Z minus half, there will be another electron, but energy is the same. So each quantum state you can fill with one electron. So you take an energy state E, lowest energy state, you put 2 electrons. Now you can't put any more electrons in the lowest energy state. You go to the next higher energy state. You can put 2 electrons. Then you go to the next higher energy state. You can put 2 electrons. So you keep on filling the state till you exhaust all the electrons. So there will be a highest energy level in which you have put electron. All energy levels above will not be occupied. So at t equal to 0, you have, starting from the 0 of energy, all energy levels up to an energy EF will be occupied. All energy levels above EF will not be occupied. So the highest occupied energy state is called EF naught. That is the Fermi energy at temperature 0. How do you fulfill the Fermi? Calculate what the Fermi energy. In each energy state, you can put 2 electrons. Between E and D plus DE, there are NEDE states. So you can put 2 NEDE electrons. You fill up to the Fermi level. So this must be equal to total number of electrons. Then the number density, number of electrons per unit volume multiplied by the volume of the box. So you integrate this and then you can find, by solving this equation, you can find the F naught in terms of the number density. So this is F naught, the Fermi energy for a free electron will be h cross square by 2m into the corresponding wave vector, Fermi wave vector square, where the Fermi wave vector is 3 pi square number of electrons per unit volume power 1/3. You please note, number of electrons per unit volume. What is the dimension? 1 by meter cube. So 1 by meter cube power 1/3. 1 by meter. That is the dimension of a wave vector, which is 1 by meter. So Kf, even without solving any of the equations, you can say Kf must be proportional to n power 1/3. So you calculate the Fermi level like this. If you have more electrons per unit volume, Fermi energy will be more. If you have less electrons per unit volume, Fermi energy will be less. Why does it get stuck? Now, how many electrons will be there per unit volume? We will make a calculation. Suppose you take sodium. You know molecular weight of sodium, 23 grams. So molecular weight must contain Avogadro number. So 6.03 10 power 23 atoms will be there in 23 grams of sodium. 1 cc of sodium, the density of sodium 0.97 grams per cc. So in terms of kilogram per meter cube, it is 0.97 kilogram per meter cube. So you take 1 meter cube, the weight of sodium is, mass of sodium is 0.97 kilogram. 23 grams contains 6 into 10 power 23 atoms. 1 kilogram you can calculate, that will contain something like 2 into 10 to the power of 28 sodium atoms per meter cube. Sodium contributes 1 electron to the conduction band, outermost 3s electron to the conduction band. So each sodium atom gives 1 electron. So the number of electrons per meter cube will be 10 to the power of 28. That is why I said you can define a number density because the energy levels will be very closely spaced and you have to put 10 to the power of 20. If you take 1 meter cube of sodium, you have to put 10 to the power of 28 electrons in various energy levels up to the Fermi level. So, if you now substitute this number in this equation, calculate Kf, calculate F naught in electron volts, then it will come to a few electron volts, 2 electron volts, 3 electron volts, depending on the number density. So the Fermi level for any metal is of the order of electron volts. What is the corresponding temperature? I can write energy also in terms of temperature by equating it to kT. kT is also an energy. So I equate it to kT. I will get the corresponding temperature, the temperature corresponding to this Fermi level. K is in electron volt per Kelvin, 88.6 microelectron volt per Kelvin, and the Fermi level is a few electron volt. So if you take 1 electron volt, TF is 1.13 10 power 4 Kelvin, 11,000 degrees Kelvin. What is room temperature? 300 degrees Kelvin. What is kT at room temperature? 20 milli electron volt. Whereas Fermi level is several electron volt. So room temperature, kT, thermal energy, is less than a percent of the Fermi energy, 1% of the Fermi energy. At a finite temperature, an energy level E can be occupied with a probability 1 by e to the power of E minus EF by kT plus 1. So at a finite temperature, you define Fermi energy as that energy E equal to EF. When you put E equal to EF, this becomes half. So occupation probability is half. At a finite temperature, Fermi temperature level is defined as the level at which the probability of occupation is 0.5. So, at a finite temperature, thermal energy can raise the particles to any energy. Of course, number of particles in high energy will be very small fraction of the number at low energy. But when you have so many particles, you can have one particle at a very high energy. So You take the total number, integrate it up to infinity, multiply NADE by the occupation probability, put it equal to NL cube. That will give you your E of t. And your E of t, you can see, is E of naught into 1 minus pi square by 6 t by t of the whole square. E of naught is the energy, Fermi energy at absolute zero, highest occupied energy. EF is the Fermi energy at any other temperature. And you see that this Fermi energy decreases as temperature increases slowly, very slowly, because T is very small compared to TF. TF is 10,000. T is 300. 300 by 10,000. 0.03. So 0.03 whole square. You can see how much is this number compared to 1. So the Fermi energy has a value close to EF naught, but comes down very slowly as the temperature increases. You can neglect the variation of EFT and say EFT is equal to EF naught for practical purposes. You understand this? I hope you do, because I can't get a feedback. Please let me know whether you have followed what I have said.
Participants can ask questions through comment box, through chat box. You can send comments
You
here.
see whether anyone has given any.
Yeah, it's open, sir. Chat box is open.
So what do you do?
They need to send comment. No, they will send it. So we need to.
What is on my mind? I want to know whether you followed my lectures. What I told you about effective mass, what I told you about Fermi level, number density of states. Have you followed? Yes or no?
Yes, sir, we follow. Thank you, sir.
Please share by comments. Please share by comments. Open your chat box and send your comments by chat box.
Oh, you have followed what I said so far.
Yes, sir. Yes, sir.
I hope so.
Yes, sir. Yes, sir. Very much.
So
In fact,
now I
yeah.
have started.
Somebody speaking.
Hello. Very much, sir. In fact, especially today's lecture. Hello.
I can
Somebody is speaking.
speak.
No, sir, just a minute. 1 minute. We'll unmute that. Comment in the work code. We can't listen. Somebody can listen.
Sir, please send your comments in the chat box. Chat box is open.
Yeah. Wait for them.
Yes, sir.
Okay, sir. That's it. Chat box.
We'll continue.
Okay, sir, you can.
You can.
Sir, continue.
Okay, then how do I press anything? Okay, I take it that all of you have followed what I said.
Shall I stop sharing the PPT? Sir?
No, he'll start. Start. Okay.
I presume all of you have followed what I said. Now I have plotted here twice N Fe, and I have plotted here energy. When T is 0, Fe is 1 up to Ef naught. It is 0 beyond Ef naught. So you see, these are give you all the states, energy states. All states up to Fe are occupied. All states above Fe are unoccupied. Whereas at a finite temperature, you find all states are occupied, but states above Ef naught are occupied by very little. States well below Ef naught are almost fully occupied. States close to Ef naught of which kT, only electrons from such states are removed and pushed to higher energy values. So you have to only, when temperature changes, not all electrons are affected in energy. Only electrons in a width kT about the Fermi level, only they are raised by thermal energy to a higher energy. This explains why the electronic contribution to the specific heat of a metal is low. If the electrons obeyed Maxwell-Boltzmann statistics, then every electron must have an energy 3 by 2 kT. When temperature changes, every electron will contribute an amount 3 by 2 K into N. Number of electrons is comparable to the number of atoms. So if we take a gram mole, number of electrons will produce an additional contribution of order 3 by 2 R. But we don't see this experimentally. We see that if we take 1 gram mole of sodium, its specific heat is close to 3 by 2, is close to 3R. This is the contribution of the atoms. They have kinetic energy and potential energy. Each one of them contributes 3 by 2 kT. So you will have 3 kT per atom. There are n atoms. So 3n kT, specific heat is 3R. If electrons also obeyed Maxwell-Boltzmann statistics, specific heat of sodium will be 3 plus 3 by 2, that is 4.5 R. But experiments show it's only 3 R, very slightly more than 3 R. The reason is electrons obey Fermi-Dirac statistics. So all electrons do not change their energy when you change the temperature. Only electrons very close in a width kT about Ef will change their energy. How many such electrons will be there? Twice Ne at E is equal to Ef. And what is the E? The width kT. So the number of electrons which are participating in contributing to the specific heat will be proportional to T, and of the order of, if you take NEF, you get in the denominator EF naught, so it is of the order of T by TF. So it is this fraction of the total number of electrons which change their energy, and this fraction is a small percentage, so electronic contribution to the specific heat is small, and each electron changes energy by kT. So change its energy is kT into T by Tf proportional to T square. So specific heat is proportional to T. So the electronic contribution to the specific heat will increase linearly with temperature and will be very small. It's a very small fraction. This was the first experimental proof that electrons obey Fermi-Dirac statistics. Now, when you take the effective mass approximation, you only change the mass. That means you are only changing the prefactor, multiplying e to the power of half. The number density varies as e to the power of half multiplied by h cross square by 2m star power 3 by 2. So this m star will change that factor, but number density near the minimum in the conduction band or maximum in the valence band will vary proportional to e to the power of half. Not all the way in the band, because this approximation is valid only for small changes in k values, only very close to the minimum or the maximum. But even in a doped semiconductor, the number of electrons in the per unit volume in the conduction band is 10 power 20, whereas the number of electrons in a metal 10 power 28. So you see the number of electrons occupy a very small region, width of energy states near the minimum of the band. And this approximation is good to describe the properties of those electrons. That is why the effective mass approximation is very useful, because in semiconductors, the number of electrons occupying the conduction band is very small. But I can understand the Fermi level in a metal because there is a conduction band, you can fill the energy levels, it is the highest filled state. But in a semiconductor, the valence band is filled. How do you define the Fermi level? You define the Fermi level in the following way. At a finite temperature, you remove one electron from the valence band, put it in the conduction band. So the energy is close to the minimum of the conduction band. So what is the probability that you fill one conduction band state is filled? That probability, according to the Fermi-Dirac statistics, is 1 by 1 plus exponential EC minus EF by KT. How have you created the electron? By creating a hole in the valence band. What is a hole? Absence of electron. So what is the probability that an electron is absent in the valence band? It is 1 minus the probability that the electron is present in the valence band. Number of electrons in the conduction band is number of holes in the valence band. This gives the probability for a hole in the valence band. So if you substitute EV, FEV, EV minus EF, that will become 1 minus 1 by e to the power FEV minus EF by KT plus 1 multiplied through by e to the power of minus E. Simplify it, that will give you 1 by 1 plus EF, EC minus EF. This will be EF minus EV by KT. So the two things must be equal. One hole corresponds to 1 electron. So they must be equal. That means EC minus EF must be equal to EF minus EV. So what is the Fermi energy? It is EC minus EV by 2. It is halfway. This 0, this is EV, this is EC. So ECEF is EC plus EV by 2. I made a mistake. EC plus EV by 2. That means it is halfway between the valence and conduction band. From the Fermi level, conduction band is Eg by 2 below the Fermi level. From the Fermi level, valence band is Eg by 2 below the Fermi level. From the Fermi level, conduction band is Eg by 2 above the Fermi level. The gap between the valence and conduction band is Eg. Fermi level is halfway between the conduction and valence band. So, if you now put that here, what will be EC minus EF? That will be Eg by 2. So, the probability of exciting an electron in the conduction band is 1 by 1 plus exponential minus Eg by 2 kT. EC minus EF by 2 kT. So it will be 1 by 1 plus exponential Eg by 2 kT. EF is of the order of Eg is of the order of 1 electron volt. Gap in silicon is 1.1 electron volt. Gallium arsenide 1.5. So Eg is of the order of 1 electron volt. So Eg by 2 is in electron volt. What is kT? 20 milli electron volt. So Eg by 2 kT, very large number. You say 1 electron volt by 20 milli electron volt. How much is that? 1 divided by 2 into 10 power minus 2. That is 50. So this will be e to the power of 50. This will be 1. 1 is negligible compared to e to the power of 50. So you omit 1. So FEC is e to the power of minus EC minus EF by kT if you omit 1. That is e to the power of minus Eg by 2 kT. So the number of electrons in an intrinsic semiconductor in the conduction band will vary as e to the power of minus Eg by 2 kT. This will change the conductivity of the semiconductor. So by measuring the resistance of the semiconductor as a function of temperature, you can measure the band gap. No, I think, yeah. But even in a semiconductor, I have not taken all the factors into account. Actually, number of electrons, energy levels which are filled in the conduction band depends on the number density in the conduction band multiplied by occupational probability. Similarly, for the valence band, number density multiplied by occupational probability for the whole. I have omitted the number density and showed EF Fermi level is exactly halfway between EC and EV. Even if you take the number density of the conduction band, number density of the valence band, it only makes a very small change. So you see that Fermi level is almost at the center of the conduction band. And as you change the temperature, it comes down very, very slowly. The Fermi level changes very slowly and comes down in silicon or in any semiconductor as the temperature is increased. Just like in metals, the Fermi level comes down very slowly as the temperature is increased. Same thing happens in silicon, but not the same expression. So I have covered in these 6 lectures, I have covered in these 6 lectures, starting from how to make reciprocal lattice, what is the importance of reciprocal lattice, why a Brillouin zone is important, because it shows the full symmetry of the crystal, which a unit cell of the reciprocal lattice doesn't, and how to construct the Brillouin zone. Then I showed what is the reduced zone scheme and what is the extended zone scheme, because if you take 2 points separated by a lattice vector, the phase of a wave is the same. So a wave vector k and a wave vector, if you take 2 points separated by a lattice vector, you take a wave of wave vector k and a wave of wave vector k plus gh. Both waves phase difference will be the same. So you can't distinguish by measuring only the phase at 2 points separated by a lattice vector. You can't say what is the wavelength of the wave. If there are intermediate points at which you can measure the phase, you can distinguish between the waves. This is possible with electromagnetic waves because electric field is defined everywhere. This is possible with electron waves because the probability amplitude or charge density of the electron is a continuous function of position. But if you take lattice vibrations, the displacements of atoms are defined only at the positions of the atoms, not anywhere in between. So for lattice vibrations, there is no unique wave vector. So you completely specify all the possible modes of lattice vibrations by confining your wave vector within the first Brillouin zone. Whereas if you take an electron, then it can have any wave vector k and k plus gh have different energies. Still you can represent the wave vector gh within the first Brillouin zone, but you can show it as a different energy. Okay, then you have a periodic potential. The periodic potential causes the energy levels to separate near the edges of the zone. So you get band gaps. And in a semiconductor, you have the topmost filled band, which is the valence band, and the band above that, which is unfilled, is the conduction band. At absolute zero, the valence band is completely filled, the conduction band is empty. When the minimum of the conduction band and maximum of the valence band occur at the same point in the Brillouin zone, semiconductor is a direct bandgap semiconductor. Optical absorption is easy in such a semiconductor. But in a semiconductor where the minimum of the conduction band occurs at a different point from the maximum of the valence band, that is an indirect bandgap semiconductor, the efficiency of absorption of light is small, therefore they are not very good for solar cell applications. Then near the minimum or maximum, we can expand the energy in powers of K. The curvature of the energy versus K surfaces is represented by an effective mass tensor. There is a tensor which has 6 components, but for simplicity, we take it to be a scalar quantity, and the effective mass for a valence band is negative, but you can interpret it as the effective mass of a positively charged hole which will move in the direction of the electric field. You can find effective masses such a large number of electrons, so you define number density of states, number of energy levels per unit width of energy. And this number density of states for free electrons in 3 dimensions varies as e to the power of half, proportional to square root of e. It increases as a parabola. Then you have to, if you are working at absolute zero, you have n electrons, you fill the electrons starting from very low temperatures and go up to a certain level, which is called the Fermi level. But if you are working at a finite temperature, all energy levels are filled, though energy levels which are very high, occupation probability is very low. You define the Fermi level as the level for which probability of occupation is half. And then the Fermi level varies very slowly with temperature. Yes. I will answer your question. This Kavanagh. Okay, effective mass of the electron, effective mass of the electron hole, same magnitude, means within a factor. I have shown you, for example, in gallium arsenide, effective mass of the electron is 0.06, effective mass of the hole 0.4. So the ratio is something like 80. So it will be within a factor of 1 to 100. The larger the effective mass, the narrower the band. Okay, all right. Yes. In fact, I have given it as a problem for you. In 3 dimensions, the number density will be proportional to the square root of the energy. In 2 dimensions, number is independent of the energy. And in one dimension, the number is inversely proportional to the square root of the energy. You please verify why it is so. In 3 dimensions, you have to draw a sphere. For that, pi k cubed. So between k and k plus dk, 4 pi k square dk. So number density varies as k square dk. In 2 dimensions, it is a circle you have to draw. Area is 4 pi k square. So between 2 such circles, it is 8 pi k dk. So it will be proportional to k. In 1 dimension, you work out how it is. Okay, finished. Okay, fine. So everyone said we have followed you.
Yes, sir.
So I don't know, because I don't know, I talk very loud. I don't know whether they hear what I'm saying.
Thank you, Professor R. Srinivasan, for your valuable time and sharing your knowledge with us and participants. Dear participants, with this we conclude day 3 and kindly come back tomorrow at 11 a.m. The link will be shared to your email addresses. Thank you.